Okay, so here is I think this is the fourth example, maybe, of class 21. And this is one out of Sham's outlines. And it's got multiple parts. It's got these two parts. This thing is pivoted down here. This guy is on a little roller skate, and then linked up right here. There's a wire, and also 1,000 pounds, now 1,000 newtons being put right here. And so they're going to cut this wire. And so they say this bar ABC is 3 meters long and has a mass of 20 kilograms, and it's pinned at the ground, and it's attached to a bar BD, which is 2 meters long and has a mass of 10 kilograms. Determine the angular acceleration of each of the bars immediately after the C is cut. Assume there's no friction at D, and that it's moving on rollers to the right. So I already have this written out. We first do the kinematics. We know that there's all the velocity is 0 at the time of release, so there's no accelerations. No normal accelerations, excuse me, because omegas are all 0. I do a little kinematics here, and I set up what the accelerations are going to be, the relationships. We do want to know the acceleration at the center of gravity of each of the parts. That's something that's going to be kind of key to how to manipulate these, or how these work, right? So we have AB right here at that point, at the junction point, is going to be alpha ABC, and it's rotating about A right here, so that we know that's what the acceleration of B is going to be, that 2 meters times that alpha ABC. And then similarly, we're going to take at the midpoint right here, so at 1.5 meters, we could find the acceleration, and I call this of G1 right there, right? And it's all tangential because there's no normal anyway. Now if we want to take for part BD, remember this is not pure rotation. This thing is translating and rotating at the same time. So we know the acceleration of B right here is downwards and to this angle of 30 degrees because it has to be tangential to B right here. We also know that D has to be in the horizontal direction. So we take our 3 diagrams and we focus in on point D, something that we don't necessarily know B yet, but we do, we kind of already have it kind of set up, so we're going to pretend like we know it. We do know its direction, we know the direction of D, so we can get a relationship of all of these directions based on these 3 diagrams. And from this, I'm going to predict that the alpha is going to be counterclockwise of this piece. Because you know this AB is going downwards, AD is going completely horizontal, so whatever happens here on the right-hand side needs to be going counterclockwise. Therefore, this has a positive Y to counteract this negative Y to make the AD completely horizontal. And so we write out the equation for this, for that corresponds to this diagram right here. And in the Y direction, we can establish Y is 0 on the left-hand side. We have the negative AB, sine of 30, and then nothing in the normal direction. I decided to make the normal one first. A lot of times I'll make tangential first. But I have 0 right here. And then we have the angular acceleration times the distance, right? So in this case it's 2 meters. And then we're only taking the sine of it, right? So we're only taking the vertical direction. So that's going to be our third equation. So we have 1, 2, and 3 equations. So far, we don't know AB, we don't know alpha ABC, and we don't know AG either, and we don't know alpha BD. So, and then right here's the AB that we already don't know. So there's 3 equations and 1, 2, 3, 4 unknowns. So we can combine equations 1 and 3. this guy right here, and this guy. So now we just have a relationship between the alphas, alpha ABC and alpha BD. And we note that based on what's written on here, that they must be the same thing, right? That's really because they're kind of symmetric. That's fine. And in the x direction from this diagram right here, we're also able to establish some other relationships. But we're introducing AD. So that's actually, we've added an equation, but we've also added an unknown. So now we can set up for the bar BD, we could do it about the center of gravity, right? So we're also going to need to know that. So that's going to add in even another variable, another unknown. I know it gets annoying, but this is the nature of trying to calculate these things. A lot of times, by the way, I'll jump ahead and say, you often will do this type of, when a problem gets more complicated, to do this in a matrix form to try to keep track of all the unknowns. When there's lots and lots of unknowns and a bunch of different equations, we turn them into a matrix, and vectors times matrices equal to vectors, because it's a very standard type of thing to do, and it's very common. You'll run into it, trust me. There's no way around it. So like in the x direction here, for the center of gravity of AGX, and I think we could probably, have applied that to multiply that by have a magnitude times the direction. But anyway, AD, and I decided that I was going to just call them alpha from now on. So that's why it doesn't have a specific alpha of ABC or BD. And this is our fourth equation. So we have a fourth equation, and then we have a in the y direction. There's not much going on right here, so we know that the AG2, that's the center of gravity here, in the y direction is going to be related to that alpha right here. So that's all. That right there is all this kinematics, and it's all just setting up relationships for the relationships of the motions that are going to be taking place. Now we go about, and for kinetics, and I do a little of the preliminary work. I can take for the bar ABC, I can simplify that and take the mass moment of inertia about A. So I use the parallel axis theorem about A, so I can get 60 kilogram meter squared. And then but for the other one, the other bar BD, I don't want to do that because it's not about a fixed point, right? It's translating and rotating. So for that bar right here, for BD, right, the sum of the forces. So here's a sixth equation, and I'm calling the force in between, the Bx, that's the pin right there, that's taking place on bar ABC. I have that in the equation, and the only thing that we're just taking, I should have written this out, or I guess I did the substitution of this right here, that we already knew that from kinematics, that it was going to be this guy right here. And in the y direction, I have another equation, right? So I'm taking here, here, and now I have in the FDY, not necessarily something I wanted, because I have another unknown. But we'll be okay with that. So I have a seventh equation. And now we take the mass moment of inertia, or some of the moments about the center of gravity of this piece. And in doing so, we don't have to put the mass times gravity in there, but we do have a Bx and a By and a Dy, right? And by the way, there's no friction going on here, so we don't have anything in that direction. So that's good. So now we have an eighth equation, right? So we have a lot of unknowns, but we could combine 6, 7, and 8 together. combining 6, 7, and 8, and we're able to establish a ninth equation, which is going to be the relationship between this by and the alpha. And now we do the kinetics about the longer link, about the big link, and take the sum of the moments about A, because that would be something. It'd be great that we didn't have to have a reaction that we don't need to know. And so we take B in the x direction and B in the y direction, right? So those are going to cause moments, and one's going clockwise and the other is going counterclockwise. So this one is positive and this one is negative. And then we also have mass times gravity, and that one is also in the clockwise direction. And by the way, right here, these are the moment arms of all of these, right? We have to take two times the sine of 60, and this one's going to be the cosine of 60 because this right here is 60 degrees, right? And then we have 1,000 right here. We have to take care of that, and that one too is going to be clockwise. And its moment arm is going to be cosine of 60, so it's the entire length right there times the sine of 60, cosine of 60. And then because we're taking it about A right here, we can take this one as a pinned. So we use the mass moment of inertia. We don't use this guy because remember, we don't double dip, right? If we're going to do something about a fixed point, right, use the equation about a fixed point, we don't also include the mass moment of inertia. We don't also include the effective moments due to the acceleration of the center of gravity. That's already been taken in account of when we had when we did the moment of inertia about A. So we could combine equations 6, 9, and 10, and lo and behold, we're able to find what the alpha is going to be. And that's actually the alpha of both of the equations. And so one's going clockwise and one's going counterclockwise. I know, it's a really, really, really long problem, but having to think through a really long problem and keep track of all of the details, that's a really important engineering skill, something that you got to get better and better at so that you can make the big bucks. You can solve the difficult problems, keep track of everything that's taking place, and apply these ideas in a logical sense, systematically, but also with a lot of mindfulness of thought of what's taking place. Lastly, this is one of your homework problems, third, so the third homework problem. So as a plus bonus to anyone who's watched this video through this, I will tell you a little bit about how to do this. This used to be an example, and I decided to make it into a homework problem. So what you would do, this car is accelerating, and we want to find out what angular velocity the door will slam shut when it hits, right? So it is moving forward. The car he maintains a constant acceleration, so he's going a zoom in that direction. And so this door is going to, hopefully it'll overcome whatever little spring kind of hinge in there that kind of keeps the door from just flopping about freely right there. There's a little bit of resistance to the motion, but it's going to overcome that, and this thing's going to gain momentum. It's going to slam shut, right? Hopefully your fingers aren't in there. And so they mean this when theta gets to be 90. Obviously, that means the door has been shut. So the secret to this is to write out the kinematics, right? So we want to know what the relationship is between the car's acceleration and the acceleration of the center of gravity of the door, right? Well, okay, so the secret to solving this is once you get this relationship set up, then set up the kinetics, but don't go to this, right here. Go to this right here and this right here, right? Remember that the acceleration that we care about is at the center of gravity, and that is a combination of translation and rotation. Okay, so we could keep the translation right in here as one of our knowns, and we have this one of these as an unknown, and this is as an unknown, right? But we can relate what omega is going to be, the omega that's multiplied by this right here, the AG with respect to A in the normal direction is going to be omega squared, and then R. Sorry about that. What the hell? And going to be times R G with respect to A, right? But if we're taking it in, if we take it maybe in the tangential direction, for instance, right here, or no, we take it in the normal direction. Yeah, if we take it in the normal direction, and we take the sum of the moments, right, is equal to about A, and sum of the moments right here, that's not going to work for us. Yeah, that's going to allow us to get what this alpha is going to be, and then we're going to be able to get it in the x direction. Yep. Okay, yeah. So I gave some hints right in there, but this is, I think the biggest hint is to leave this alone, right? To not go to here, to keep them separated like that. So anyway, that's hopefully that'll help you as you go through. And what you want to try to do is establish what an angular relationship to this, and then you can like integrate it to be able to figure out what it's going to be when it reaches 90 degrees. You're able to figure out what the angular velocity is going to be. You'll work out backwards. So hopefully that helped. We'll discard all that stuff, and we'll upload this video, and then gotta get some other